My name is Noori, and these are my colleagues, Sumit, Muhammad Ali, and Arsalan Najmi. Our faculty supervisor is Dr. Gerald Cook, and our co-advisor is Dr. Nguyen, and we present to you Power Walk. The average person takes roughly 3,000 steps every single day, thus creating a lot of mechanical energy. Energy harvesting is a process where we store that energy that normally would be wasted, and we convert that into stored energy that we could use as electrical energy. Now the question arises, why do we need an alternative source of energy? There's an increasing demand of energy, which is directly proportional to energy costs, and it also allows devices to be completely portable. This is a map of Europe. It's kind of dark to see, but this is a map of Europe and North Africa. As you can see, in Europe, it's heavily lit. 90% of Europe have access to electricity in homes. When you look at Africa and the sub-Saharan region, there's a limited energy in developing areas. What we did is we did a closer look in the three countries that we were representing. In Afghanistan, according to the IEA World Energy Outlook, in 2001, only 6% of homes had access to electricity. 10 years later, in 2010, that number only inched up to 10%. India, which has the second highest population in the world, only 48% of homes have electricity. Now, there's also a problem in more other areas in Europe and America. The problem is mobility. With more technology, everything needs to be charged every single day. And do we actually need to be at home next to an electrical outlet to charge them? What we've done is that we built a device which would generate electricity using simple human motion, and it's also minimally intrusive. The power generation device will be used to charge different household devices, such as phones, cameras, and other remote controls. Also, it will have the ability to charge different batteries, AA, AAA batteries. More importantly, it should be light in weight and portable. And we want to make this as low cost and economical as possible.
Our approach, we use Faraday's laws to state that electric field can be created by changing the magnetic field. For that, we did a prototype, we had a small cap, we put a magnet inside it, and we put a copper wire around it. So every time you shoot the magnet, it creates sparks, and every time the magnets move back and forth, it creates voltage. So the faster you shoot the magnet, the more voltage it's going to produce. And this is our design for research. As you can see, there's electric meter. As you can see, electric meter produces 5 volt rate voltage at a rate of 800 milliamp current. It goes through a rectified circuit which converts AC to DC voltage, and then we have LED across it. If it lights up, that means it's working. So if it's not, you have to make sure connections is right for your emitter. And then it goes to a voltage regulator, which regulates your voltage to 1.2 volt. And then you can use that to charge your batteries, and which after that we put that in a voltage booster circuit, which is going to boost your voltage up to the 5 volt, and you can use that to charge your devices like for iPhones and Android devices. And this is a circuit we use. We have 4 diodes across it, so you can see those 4 diodes is a full bridge rectifier. It converts our AC voltage to DC voltage. And then we have a capacitor across it. We use a big capacitor, which is plus 1,000 microfarad. It reduces the recoil across the circuit. And then we have a resistor and the LED across it. Like I mentioned before, it's if it lights up, it means you're getting voltage from your generator. And if it doesn't light up, you have to make sure the connections are right. And then we use a voltage regulator, which is LM317, it regulates our voltage down to 1.2 volt. And the magnets we use a magnet inside the electric meter. The magnets were neodymium magnets, and they were D500H. They had surface gauge of about 44. They weigh about 1.7 ounce, and they have 1 inch diameter, and they're about 1/2 inch thick. These magnets are really strong, so we had to be careful when we were handling it. So one of the interesting facts about these magnets are they can hold up to 40 pounds of steel. And we used a voltage booster that was a chip MX 756. It boosts our voltage from up to 5 volt, and it breaks down up to 0.7 volt. Has a maximum frequency up to 500 kilohertz, and has boosted current up to 60.
Alright, so essentially PowerBook is a device which has four main functionalities: generation of power, conversion of power, storage of power, and boosting of power if needed. So for the first step, the generation of power, we built an electromagnetic generator which was 11 inches in length, as you can see in the picture, which was wrapped with 750 feet of fine copper wire, which has about 1,000 turns in it, and about 25.3 ohms of resistance. The frequency that we measured while jogging was 2.5 hertz. Why we said that frequency at 2.5 hertz is power walking is because of the AC voltage intensity over there is 6.04 volts. And that's exactly what we needed for our LM317, because LM317 requires its input to be 3 volt higher than its output. And as you can see, this is output voltage from the generator that we generated while shaking the generator. And you can see the fluctuations because it totally depends on how you're moving the generator, how fast you're moving the generator, and how the magnets are moving inside. The testing process, the electromagnetic generator was tested by varying 7 different parameters: the number of magnets, the strength of magnets, the number of pole windings, length of cylinder, and of course the frequency. The frequency, as you are increasing the frequency, the voltage is going to increase. But the most important factor in this project was the length of the PVC. If the length of the PVC, which is the cylinder that you're using, is shorter, you're not going to get the voltage. So we used 11-inch PVC pipe with about 1.125 inch of diameter. The number of magnets were 4.45 Tesla, which is very strong. And the number of windings, we reduced it down to 1,000 to reduce the resistance and increase efficiency. For the circuit, we had a full-wave bridge rectifier, which has a voltage drop of about 1.4 volts. And in order to reduce the ripple voltage that's coming out from this AC voltage, we either has to use the capacitor or the resistor that was large in size. Now we chose to use the capacitor because it would minimize the loss of current and to store the charges temporarily. So the RMS value that was measured was 6 volts, and peak-to-peak voltage was about 7.9 volts. This was the schematic that we designed. This is just for the rectifier circuit in PSpice. This is just basically to illustrate that with the capacitor value of 47 microfarad, you're not reducing the ripple voltage, so it's useless. With 1,000 microfarad that we use, you're getting a DC voltage out of it, and the capacitor value is calculated using the formula 5 times I, where I equals to the load current. Time constant that was calculated to be was 1 millisecond, which is pretty good. The voltage booster, this is when the user decides if he wants to use it or not. So if the battery is enough, so if he's charging like low power devices like flashlight or anything, the batteries can be used. If he wants to charge an iPhone or iPod, then he can plug those batteries that are already charged from the circuit into the voltage booster circuit to get the 5 volts, and simply charge the iPhone or the Android power devices.
I'll be talking about the batteries we charge from the generator that goes through the circuit. We charge 3 different kind of batteries: AA, AAA, and D-size battery. First, we have twin AA batteries that provides 1.2 volts, that has 23 milliamperes per hour, and you can calculate the power by 2 times the voltage times the current, which is 5.5. So the twin AAA and twin D batteries, they'll have 1.2 volts and it's 2,500 milliamperes per hour and different volts. And the picture shows all the type of batteries we use. We have AA, single AA, twin AAA, and D-size battery. So we charge AA and AAA batteries that were used to store the energy, which in turn would charge the devices like we mentioned earlier, like iPhones or iPods. The circuit was tested using A, AAA, and D batteries. It was concluded that the lower the current requirements, the less time it would take to charge the battery. So this graph shows that we use a drain AA battery or drain AAA battery, and we charge it up to 5 minutes. It goes up to 1.2 volts, and we keep charging it up to 20 minutes. We concluded that the voltage of that stays at 1.2 volts. To fully charge a AA battery, it takes up to 6 hours approximately. Same thing applies for AA batteries. It stops at 1.2, so no matter if you test it after 10 minutes or 20 minutes, it will stay at 1.2. We charge these 5 devices: iPhone, digital camera, Xbox, MP3 player. All the charging time for these are 20 minutes, and the usage time varies. This is our final design for the circuit. We're just using a Vaser vector board. The inputs are the two blue ones on top, and then it comes with a capacitor and the LN chip, and these two, the white ones, are the output. And on the flip side of it, on the bottom, is a voltage booster on the vector board as well. So we have connected a AA battery that's going into the input, and output is basically charging a 5-volt device like an iPhone. This is a full design with 2 generators on the side. Like I said, the input is the blue ones going through the input, and each generator is charging a single battery. So we have 2 batteries, 2 generators, and that's a full circuit. I would like to show you a video, and a real life video, what can you do with a generator in the circuit. I was looking for sound. Can you come? Oh, it's background music. It's a good part. Okay. Oh, what you're seeing right now is basically, I was talking on the phone, my battery died, so I had a generator in my backpack, and the circuit. So I just basically strapped it on. Now you're gonna see time for a jog. I'm just gonna go outside. Basically, I left my phone charger at home. I have no other way. Outside. I'm coming out now. Tired. Now, as you see, I'm going to take out my iPhone, and it's going to be charged. So iPhone is good to go, and basically you can resume my conversation. And this is the second part, the second short video, basically demonstrating the detail version. Like 2 people shaking the generator. It's charging a AAA battery. I'm going to put it in a flashlight. As you see the battery charge, the flashlight will work. It turns on. Okay. So I'm going to take the same batteries, charged battery. We're going to flip the circuit, which is a voltage booster on the bottom. So the same output of the battery that was charged is going to go into the input, and the output is going to be a 5 volts. So you can use a 5 volts as any other device, any USB, like a PDA phone. We're going to have an iPhone, for example. As you see now, the charge goes in. You'll see the picture of an iPhone. The thing will light up, and it will say charging right there. And we'll show some tips, like the little the connectors in the front that you can also charge besides the iPhone right there. So you can, if you have a Droid phone or any other kind of phone, that will work as well.
This is the schedule of some of the chart of our schedule and some of the milestones that we've hit. Funds spent. We were trying to make Power Walk as economical as we possibly could. It came out to be about $125 for everything. We put about 250 man hours into the experiment, so the total cost came out to be $9,000. Individual contributions. As project manager, I was in charge of generator design and system integration. Muhammad Ali he played 2 hats in this project. He was our technical supervisor as well as our financial manager. And he was also responsible for the generator design. Sumit, our research supervisor, was in charge of vector board designing and circuit implementation. And Arsalan, Najmi, our superstar of the video, was a development supervisor. He was in charge of power management as well as the circuit implementation. Some of the lessons that we learned and some of the skills, vector board designing, none of us had any of the skills beforehand, so it was good that we got our hands on that. Also, worst case scenario for any design should always be taken into consideration before actually implementing the design. So you shouldn't hope for the best, but you should always prepare for the worst, and that will always help you out. Patience and perseverance during testing and experimentation, that was the key. Dr. Cook met with us over the summer, and we were struggling with the generators. We must have made probably 40 generators, and each one takes about an hour to make. And he mentioned to us that Benjamin Franklin, when he did his kite experiment, he must have done it 255 times until he finally got it to work. So had he stopped earlier, we would have never got his results. So we use that as motivation, and we work through the long summer days and the long cold autumn nights. Special thanks to Dr. Cook for helping us out, and we want to especially thank Dr. Lee for funding this majority of our project. He helped us out with the generators. We also like to thank Dr. Brian Mark and our teaching assistant, Avik, who is not here today. And these are some of our references, and this concludes our